now we move on to our last but not least speaker, Professor Karena Chapman. To tell you a little bit about Karena, she's now the Joseph Lauher and Frank Fowler Endowed Chair in Materials Chemistry in the Department of Chemistry at Stony Brook University. Before that, she was a chemist at Argonne National Lab. Once again, she was our neighbor, building a dedicated pair distribution function instrument at the Advanced Photon Source. She received her undergrad and grad from the University of Sydney in Australia. Her research focuses on understanding the coupling of structure and reactivity in energy-relevant materials using advanced synchrotron-based characterization tool. She's currently engaged in projects in battery electrodes, battery electrolytes, nanoporous materials for catalysis, and new synthesis. She got many awards. A couple I will mention here. She was recognized as one of the American Chemical Society's Talented 12. For everybody on this audience knows how this is not an easy one to get. There is hundreds of applications and nominations, and they only pick 12 a year. That speaks loud on how talented Karena is. She was also awarded the 2015 Amaris Outstanding Young Investigator Award, and she is now the Deputy Director of an EFRC Genesis, the Next Generation Synthesis Center, which funded by the DOE. Karena, it's all, please go ahead.
Thanks, Omar. And good morning, or good afternoon, or good evening, everyone. Let's see. I'm going to assume this is sharing. Okay.
No, we see your presentation.
Oh, okay.
We see your presenter view.
Yeah. So presenter view and slide view. You get a preview of all my next slides. How's that? Is that better?
Better.
That's good.
Perfect. Okay. So today I'm going to be telling you about how we can use high-energy X-rays to characterize the nanostructures of materials, a whole range of materials that are relevant for clean energy applications. And so these are types of systems that are inherently dynamic, and they can reorganize and restructure as we're actually using them. And so probing the atomic structure in situ during the reactions or the applications is really important to understand what the actual structure, the real structure-function relationship is. And so that's important to serve as a roadmap so we can design the next generation of materials with even better functionality for clean energy. Or if we take into account the previous talk from Lauher, this gives us a sort of verified structural input that can be used for calculations that are going to be more representative of what's happening in the real material system. And so we've heard a lot today so far about porous materials, both COFs and metal organic frameworks, but I'm going to be talking about these systems, but also a broader range of nanomaterials in general, to give you an idea of the generality of the challenges and also of the opportunities in terms of understanding these types of systems. So as I said, nanomaterials are central to so many different applications that are relevant to clean air and clean water and clean energy. So we've heard a lot about sorption and separation so far today, but if we think about the catalysts that are responsible for converting CO to CO2 in your catalytic converter, or if we're thinking about the electrode materials that are sitting in the batteries in your cell phones, all of these types of material systems involve nanostructured materials at some scale. And so the challenge in these systems, and to be able to understand why a material is, perhaps why it fails, comes down to understanding the nanomaterial structure. And these systems are, well, none of them are in the thermodynamically most stable state. And so these systems can restructure as we're using them, and they can evolve. And understanding that those dynamic structural changes are important to being able to understand what is that active state. So what is the active state of that catalyst? Is it what you're seeing as rest, or has it restructured in the reaction environment in order to give you some kind of different attractive functionality? And so given the dynamics of the system, this sets up a sort of a Schrodinger type of problems. How do we actually measure what's going on in this operating system and look at these dynamic nanosystems without actually changing and compromising the state of the system itself? So if the observation changes what we're looking at, that's obviously a problem. The second challenge that we're facing in terms of understanding these nanostructured materials is that, I think as Professor Banerjee mentioned earlier, we need crystallinity in order to know what we have. So in order to use single crystal diffraction to identify where all the atoms are, we like to have nice crystalline materials. And obviously, as we start to look at some of these nanostructured systems, we start to degrade the crystallinity. And if we're looking at a Bragg diffraction, we might be looking at something where we have diffraction peaks that are on the order of 10 degrees wide. And so we can't get a lot of structural information in that way. And so the solution to both of these challenges relates to using high energy X-rays. And so we're very familiar from a medical perspective in using high energy X-rays in order to look at an operating system and try and identify why something might be working and why something might not be working, and what is the nature of that structure. And so the important thing is the high energy X-rays can penetrate the system without changing it in itself. And so before you actually go and reach for your keyboard and start typing a question like high energy X-rays, surely that means that there's more damage, there's more propensity to change what's going on in the system. Actually, it's the opposite, because a high energy probe means that it's very penetrating. It goes through the material and has very little interaction. So that means there's less absorption, and if there's less absorption, there's less energy that's transferred to the system, and so you don't end up getting damage. And so in the same way that you use high energy X-rays for medical imaging, we can use high energy X-rays to look at functional nanostructures as they're reacting, as they're operating, in order to understand what makes them work. And so the second piece to the puzzle is that these high energy X-rays also enable certain methodologies that allow us to look at nanoscale structures and be able to do crystallography for these very uncooperative type materials. And the tool that we use for this is called pair distribution function. And so some of you may be familiar with this, and we'll know that I'll show you quite a few of these types of data as the talk progresses. But if you're not familiar with this, it's fairly intuitive to understand what we're looking at once you know a few of the background things. So the pair distribution function is effectively related to histogram of finding atoms at a given atom distance. And so it's a function in space, so it's distance, and when we see peaks that correspond to an increased probability of finding atoms at that distance. So immediately you can take away that this peak tells you something about the atom distance, gives you the bond lengths. And I should say this is the PDF for a 2 nanometer face-centered cubic nanoparticle. So we can see our bond lengths here. The intensity of those peaks tells you about the concentration of that atom-atom distance. So that might be the coordination number, or it might be the number of electrons involved. The width tells you something about disorder. So if you've got a distribution of distances, you're going to see a broader peak. And the largest length scale at which you see well-defined peaks, so in here it's about like 18 to 20 angstroms, that tells you something about the coherence length, so how big that nanoparticle might be. So put all together, there's a lot of rich structural information here that we're getting out of our high energy X-ray scattering measurements on these nanomaterials that can allow us to understand how they are restructuring under operating conditions. So I'm going to start with some examples related to some of the materials we heard about earlier. So understanding moths, and in this case, this is considering the applications of moths as next generation catalysts. And so this comes from part of the impetus behind this research is to be able to develop new catalysts that can generate all the chemical feedstocks, all the chemicals that we're interested in, by using small molecule hydrocarbons from the natural gas that's become much more abundant, instead of the traditional approach, which is breaking down oil and fossil fuels into the small molecules that we need. So we need more efficient catalysts to do this. And the Moths are attractive as a platform for developing such atom-specific catalysts, because we have these well-defined structures with well-defined active sites that gives us opportunity to characterize and then ultimately predict with perhaps some kind of simulations or computation what might be the structure of an optimized catalyst. The example that I'm talking about today relates to the Nu1000 Moth, which those of you who are sitting here at Evanston may be able to tell you what the atomic coordinates are of each of the atoms in this particular moth. But for everyone else, this is a moth that's made with zirconia nodes that are connected by the pyrene-based carboxylate ligands to form a moth with a series of hexagonal and triangular channels. And this, because we've got these very robust zirconium-oxygen bonds, we have these very robust nodes that form the basis of this moth, which means that this moth can tolerate relatively extreme conditions, which gives you new opportunities to both chemically functionalize it and utilize it for catalytic reactions. And one of the early observations on the system was that the functionalization and the subsequent catalytic activity depended on the thermal history of the moth itself, so whether it had been heated or not. And in this case, if you heated it, it was 20 times more active for the catalytic decomposition of chemical nerve agents than it was previously. And so if you were to do the diffraction analysis and you have a look and try and understand what's changed in the structure, you can see that it's very stable. We've got these strong zirconium-oxygen bonds. These are the rocks of the moth world. But there's no obvious changes to the crystal symmetry. We can still see all the peaks. No changes to the structure. There is perhaps a bit of a broadening of the peaks. But if we start to look at this from a local structural picture, we can have a look at what's going on with that using the PDF. And so here's the PDF for Nu1000. We have peaks that go at a long distance as consistent with having an ordered crystalline material. And then if we look down at short range distance, we can recognize a peak at about 1.5, that's the carbon-carbon bond length. You can see a peak at 2.1, that's the zirconium-oxygen bond length. And we can see a peak at 3.5, that's the zirconium distance within these nodes. And so if we have a look and we do that same kind of measurement as we did with diffraction and have a look at what happens to the local structure as we heat it up, we can see that there's a very clear and irreversible change to the local structure that can be described as going from a single zirconium distance in a symmetric node to having now two different zirconium distances within a distorted node itself. And this is an irreversible transformation. And the nice thing about moths is, of course, this node is not only a feature of Nu1000, but it's found in a wide range of other metal organic frameworks. We could also make similar structures with hafnium analogs, or we can look at isolated clusters by themselves. And if we look at a broad range of these systems, we can see that this type of distortion, and here I'm now showing you the difference plots, so it just shows you how it's changing. But we see the same changes as a function of heating in all these systems, which really tells us that this is something that's common to the zirconia node or the hafnium nodes in these systems, and it's not specific to the Nu1000 Moth. And so if we think about what we know about zirconia, we know that zirconia undergoes transitions between cubic, tetragonal, and monoclinic forms at very high temperature in the bulk zirconia. That involves some kind of distortion of the structural units, so a lowering of the structural symmetry. And if we compare the kind of local structural changes associated with that transformation in the bulk system, it's exactly the same kind of structural transformations as we see in the moth system itself. And so effectively, what we can think about these moths as being is the smallest possible nanoparticles of zirconia. And it can undergo the same kind of transformations as you can see in bulk zirconia, but these can happen at much, much milder temperatures. And these transformations can be really important to understanding the catalytic activity of these systems. So of course, Nu1000 is a very interesting moth in and of itself, but one of the great attractions to this system as a platform for developing catalysts is being able to functionalize the surface of that moth with different species. In fact, you could consider putting any metal species on the surface of that moth and tuning the catalysis for different application. And here's an example where, and this is materials that were prepared by Omar Farah's group, where they put copper on the moth. And so we can see where the new bonds that are associated with the copper being deposited on that metal organic framework. We can have a look using the powder diffraction. We can get an idea, rough map of where that copper material is within the pores. And so this system itself, as it's prepared, it's not catalytically active. But if we start to activate it by heating it under a reducing atmosphere, it becomes catalytically active. And if we look at the structural changes that are associated with that, we can see that we retain the crystallinity, so the overall moth structure is retained, but we see some changes in the lattice parameters, so we see some flexing of the lattice. And if we look at the local structure, instead of just seeing copper interacting with the nodes, what we start to see is the formation of copper nanoparticles that are associated with that catalytic activity. And we can fit a structural model to that PDF and pull out what the particle size is of those copper particles that we're forming. And we can see that we have both 4 nanometer particles and we have 1 nanometer particles, or sub 1 nanometer clusters in there. And these are presumably confined by the moth framework itself. So the moth is stopping these copper nanoparticles growing larger. And so we can look at where these are. This is what I was talking about, mentioned a little bit earlier, using the information from the powder diffraction data to pull out a rough map of where the supported guest species are within the moth. In this case, it's copper nanoparticles, but you can also do this to look at where the gases or guest species are binding within the moth structure. And we can see that as we reduce it, we go from having our copper species attached, closely associated with the nodes, to then going into this larger pores. And in the end, we end up with our copper species, both in these large hexagonal channels and in these smaller triangular channels, which really goes to show that because we've got this bimodal distribution of pores in the moth, we're getting a bimodal distribution of the copper particles that have been confined by the moth. You never get a bimodal distribution of sizes by accident. And so this gives us the opportunity now to say, okay, how can we tune the structure of the moth to perhaps then tune the distribution of the particle sizes, so we can start to explore, is it these small, perhaps 12 to 20 atom clusters that are responsible for the catalysis, or is it these larger nanoparticles that are about 4 nanometers in size that's responsible for the catalysis? So having this observation allows us to now ask the next question as to how to then optimize the functionality. So moving on to sort of more, I say, traditional supported nanoparticle systems. All of you who drive a car will have, not a fully electric vehicle, all of you who drive a gas car, petrol-driven car, will have these types of nanoparticles, supported nanoparticle systems in your car. And so in your catalytic converter in your car, you have platinum nanoparticles that are supported on some kind of alumina support that's responsible for taking the CO from the incompletely burnt fuel and converting it to CO2. This is one of the more expensive components in your car because it uses platinum. And eventually, ultimately, these degrade and you have to replace your catalytic converter. So understanding this reaction, what's the nature of the actual active species, and trying to understand how to mitigate the deactivation of the system is important. So we wanted to understand what's the active species, the active nanoscale species in your catalytic converter. And so we can do an in situ reaction on this system, looking at the PDF of the nanoparticles when we're looking at different environments. So one which is CO rich, so it's incompletely burnt, so you have a lot of that active phase there, and one which is oxygen rich, where you're converting less or converting more of the CO to CO2. And we can see overwhelmingly we get the same kind of, if you squint, these are all about the same PDF. So we have the same sort of 2 nanometer nanoparticles in this system. They're all face-centered cubic. But if we start to quantify everything we can quantify in the system, which is always a good strategy when we don't know exactly what the answer is going to be, we don't know what we're looking for, we can start to see, we quantify the peak area and the peak position. And we can see that if we're in sort of higher order shells, there's no strong correlation between the area of that peak and the position of that peak. And it's only in this first shell where you have a clear correlation that you have an increased area and it shifts to higher distance, or you have a smaller area and it shifts to shorter distance. And so if you can think about all the atoms in that nanoparticle, the only way you could have something where you have the shortest bond length change in distance, but every other bond length not change in distance, the only way you can have that is if that change is localized at the surface and it doesn't propagate throughout the bulk structure. And so this tells us that we've got some kind of different surface structure that's associated with this different activity. And in fact, we can correlate that different surface structure to an increased CO2 production in the system. So we know that this must be the active phase. And so if we start to look in this a little bit more closely, we can see that there's this feature at 3.3 that's not part of the normal FCC structure that's associated with the increased CO2 production. So this is the active phase. So then we can go through and take this oxygen-rich PDF where we can see that peak, and we can go to this CO-rich PDF where we don't actually see that feature. So we don't presumably have that phase on the surface. And we can subtract one from the other and effectively isolate the contribution from the atoms at the surface. So do a sort of surface differential analysis. And when we do that, we get this kind of differential here. And we can see a peak at 2.6, we can see a peak at 2, we can see a broad peak at 3.3, which is what we were able to make out in the whole nanoparticle structure. And when we try to fit various structural models to that, it turns out that this surface structure looks a lot like a platinum oxide structure at the surface. And a platinum oxide structure that's sort of relaxed away from the surface of the nanoparticle itself. And so this tells us that this is the actual active species in the system. It's something that we're able to see in, this is, I think, measurements that were sub-second, 1 second exposures on industrially relevant loadings. And you can see features that are very similar to the features that people have seen using surface science methods. But those systems were under ultra high vacuum. They weren't nanoscale, they were idealized surfaces. Here we're looking at the real, somewhat dirty system, but able to extract out that meaningful information about how these nanoparticle structures are evolving. So moving from fossil fuel driven vehicles to sort of, okay, what's the next generation? Obviously, there's a lot of interest in developing electric vehicles that are run by batteries. And as anyone who's had like their cell phone for a year, 2 years, and starts to notice that the battery life just isn't as good after a couple of years as it was when you first got it, that same problem applies to cars and vehicle applications. And so, of course, there's a big draw to being able to develop batteries that will last a whole lot longer and have a much longer lifetime. This is also important from an environmental perspective, because the mining processes that are used to get the resources that then go into those battery electrodes can be not very environmentally friendly. And so when people are traditionally looking to understand the battery life, and what you see is you can cycle your battery, and progressively over time you lose capacity and eventually the battery might fail. The standard approach is to perhaps do some kind of operando X-ray characterization measurement during the first couple of cycles, have a look at the structural parameters, and then extrapolate from 2 cycles all the way to 500 or 1,000 cycles to try and figure out what then broke and what changed in that battery as it's cycling. And part of the reason for this is because it's just challenging to characterize these type of operando systems. As if you don't have a well-designed experiment, if you're using low energy X-rays, if you don't have a well-designed in situ cell, what you're looking at underneath your window, your X-ray window, might be at a very, very different state than the rest of the electrode. And so if you want to start to look at the changes that evolve over hundreds of cycles, you need to have a very high fidelity cell. So you look at the changes that are because of the material and not because of how you made your observation and how you did your measurement. And so we put a substantial effort into designing an operando cell that will allow us to look at these sort of longer term battery type measurements. And instead of just looking at the first cycle, we looked at the first cycle, a few cycles. We also looked at after we'd cycled the battery for 3 months. And at this point, it lost about 20% battery life. So I know this has primarily been an audience with a background in porous materials, but battery materials are just like a porous material. You're putting something in and out. You're putting lithium in and out of channels or absorption sites. The only additional things that we need to think about when it comes to making sure this battery is going to work is that you've got an intercalation material where you can change the oxidation state of that host material, and you need ion conduction pathways to get the lithium in and out, and you need electron conduction pathways to get the electrons in and out. And that's what we need for our battery to function. So if we take a system, this is what would be in a majority of electric vehicles today. So NCA, which stands for nickel, cobalt, aluminum oxide, has a layered structure. And this is one of the most common active battery materials. And it has a structure that looks like this. But when you're looking at the particles and they're actually being made into electrodes and they're assembled into cells, you actually have these polycrystalline aggregates. So you have one single crystal that's intergrown into another that's intergrown into another. And so if we look at, do a diffraction experiment on this system, we see a 20% reduction in capacity, but there's no change in the crystal structure. There's no change in where we have to model the ions. We haven't lost any material itself. We've just lost capacity. If we look at the diffraction data, we can see that we start between the first cycle and say the 93rd cycle, we start to see intensity in our diffraction peaks as a midpoint between the two extreme states of lithiated and delithiated. And the fact that it's in an intermediate spot suggests that it's got an intermediate lithiation state. So we can see that structural changes in the change in the end member. But the important thing is the operando type measurement. We can see how that energy storage reaction itself has changed. And what we see is we can see there's a population in there of those electrode particles. Nothing has changed. It charges and discharges in the exact same way as it did initially. And you can see that as the diffraction peak moves to the right and to the left as you put lithium in and take lithium out. But we can also see that we end up with this second population of the electrode. So it's shown here as the second peak here. And it's also highlighted here in this blue marker that shows the peak of that peak. And it seems the lithiation state and the reaction state of that always seems to lag behind that of the active initial population. And the distribution of lithiation that you can see here quantitatively matches how much capacity we've lost. The fact that we have this sluggish population is just the exact amount of capacity that we're missing. And so a bimodal distribution in my mind is never accidental. It's not because we have a distribution of states within a particle. It's not because we have a distribution of states across the electrode. We decided it's because we have a distribution of states within that polycrystalline aggregate electrode particle. And if we take some X-ray microtomograms that allows us to look at that nanoscale structure, well, we can see that following repeated cycling, we end up with fracturing throughout that. So we have intergranular fracturing. And what that means, and that happens as we put lithium in and out, and we have contraction and expansion and contraction, and we get a failure at those grain boundaries, which are held together more weakly. And so what this means is that the granules that are outside of the particles are just as well connected in terms of the ionic conductivity and the electronic conductivity as they were at the beginning. But the particles inside, once you start to fracture, they're no longer as well connected to the outside particles. And so they're not getting their lithium in as quickly, and they're not getting the electrons in as quickly. And so the reaction kinetics you see in that are much slower. And so what this tells us is that's kind of intergranular fracturing of that nanostructure is really important for the lifetime. And if we want to start to engineer systems that are going to last for many more years, so we don't have to keep taking new natural resources to make our batteries, then we need to think about that microstructure and perhaps optimize, the overall small particle size, primary particle size versus the secondary particle size. Okay, so I want to take the last 90 seconds that I have left to talk about sort of a newer direction that we're taking in terms of in nanomaterials, understanding nanomaterials. And that is to understand how these nanomaterials form and how those nuclei can be purposefully modified in order to get something new or access a new state. And this brings up a really challenging question, and I'd like to think about it for a bit, is how can we use a measurement that takes minutes to identify some kind of intermediate state that only persists for less than a second? So minute measurement, sub-second state. And so this is effectively a new approach that we've been taking to enhance the time resolution of our PDF measurements, which are limited by the signal's noise, by spreading out our reactions in solution over space. So we can mix our reagents at some initial time point, and that'll be time 0 in the reaction. And then the reagents flow along some kind of flow path. And depending on where we probe that reaction, that's giving us a different time point in that reaction. And we can end up sitting at any particular position in space for a minute or an hour or whatever it takes us to get sufficient signal noise to understand what's going on. And so we've started to apply this to try and understand the assembly of iron sulfides, which are important to the global sulfur cycle, but it's also a principal cause of iron corrosion or steel corrosion in wastewater treatment plants and in oil and gas plants. And so we're looking at the formation of iron sulfide, which in this case, under these conditions, forms a McKinowite, so it's a layered type structure. And with these sub-second measurements, we can start to see the formation of individual layers, and then potentially how they start to stack and then form that structure. So if we can isolate this kind of intermediate, that's perhaps one layer, we can start to think about how we can say, okay, control the assembly of that nanostructured phase and perhaps interleave different compositions or things of that type. Okay. So that's a really exciting new direction and that we're taking. And allows us to push the functionality of both the materials and the methodology. Just to summarize, I've been able to show you that the nanomaterials characterization challenges can be effectively addressed using high-energy X-rays, because it both allows us to look at dynamic states without perturbing that state, and it also allows us to look at the atomic state structure using a PDF-type analysis. These are even more valuable when we start to do them under in situ reaction conditions, and we're poised to move from being able to not only characterize and understand the structure of the material to start off with, but understand the relationship of that structure to the functionality, and then ultimately being able to use that to then control the structure of chemistry for new clean energy applications. So with that, I'm going to put up, well, my contact information is on top of there, but these are the people that contributed to this work. And I'd be very happy to take any questions.
Thank you, Karena. All right. Do we have any questions from the people who actually can unmute themselves and ask the question? Okay, if not, I'll, so Karena, the first question says, how's the distortion of the zirconium node in Nu1000 coupled with its dehydration?
That is an excellent question. I perhaps didn't show the information on that, but certainly as you dehydrate it, you start to see that distortion. Now, if you put water back on, that you get that to be reversible. So the distortion is coupled to the dehydration, but it's not reversible if you rehydrate it, at least under short timescales. I would imagine you'd have to put some kind of pressure in order to get it to revert back to its undistorted state.
Another question says, have you investigated the dehydration, the degradation mechanism of batteries with single crystal cathode materials?
Have I personally done that? As in not particle morphologies like that? No, I haven't done that. I mean, I think there can be different things, and so I think the mechanisms are different. So you can start to get surface effects, and it obviously depends on the chemistry. The thing is that it's these aggregate particles that are technologically relevant. If you start to have single particles, then you can't end up having the type of connectivity and the type of density you need to have a practically applicable battery. So it's conceptually possible to start to look at these things, but the technological relevance becomes more questionable.
And the last question, I'm not really sure if that was for this talk or not, but I'm going to ask it because it seems like the person who wants it is really persistent. The moths, which are familiar for CO2 conversion catalysis, can be used for CO2 absorption applications also? I'm assuming this question maybe was for Laura, but...
I would have to say, if something is going to be used for catalysis and you're using a porous material for catalysis, then that gas has to be absorbed in there in the first place. So you have to be able to get the gas in, but you don't want it ever to be absorbed too strongly because you'll never get it out, and then you'll never get another cycle out of your catalyst. So I think there's a balance there in terms of what's good for catalysis versus what's good for absorption.
Okay, Sanbin raised his hand. So Sanbin, you could unmute yourself and ask the question.
Okay, so hi Karena, I was interested in the lithium battery, the pic that you talk about sluggish. So you see structure. How big do you think these sluggish particle picks are before you can see them? Like, are they comprising roughly like 1,000 lithium ion that you can actually see that? What if they are smaller? They start forming smaller one, like 100 lithium ion. Then I'm interested. I guess I'm not asking the question very well. Like, how big do these particles, the sluggish particle, have to be before you will see the structure in the pic, in the spectrum?
So I'm not sure if I got the question right, so tell me, you can stop me if I'm not right. So I think the question is related to what's the particle size.
Yeah, what the particle size, yeah.
So these in these particular case, they're on the order of about 200 nanometers. So they're fairly large particles. The sluggish particles are not a different size in this system that we're looking at. They're not ostensibly a different size from the particles that were active, but they just happen to be on the inside rather than on the outside of that polycrystalline aggregate.
Yeah. So I guess I must have missed something then, because I thought when the lithium ion coming in and out of the cathode, right? Then during the transport they move, ion by ion, right? And then so basically when they move, they would have a tendency to reform as a particle, at whatever the place that you had inside a cathode, or they can maybe dock onto some other side of the cathode and start forming a different particle. So is that a reasonable question or not?
I don't know, are you talking about where the lithium goes?
Yeah, because of where the lithium gets transported, right? Because they transport from one place to another. Do they always go back to the same place that they originated from the particle? Can they actually go to some other place and form new particle, and therefore you start seeing, some of these newly formed thing is being sluggish because like they are trapping inside, what I call like maybe a deep well and they cannot get out. So I'm not a battery person. I'm just actually thinking about it that way.
So maybe we can think of it, you can think of it as your porous moth, and you think of it as your guest molecule going in and coming out. So it's going in, it doesn't necessarily go back into the same host.
That's exactly.
But it's not forming another crystal off by itself. So it's still, it always has to go into that host material.
Okay. But they don't go into that host material in like a different location that may trap it, tighter, and it cannot come back out.
That is always one of the potential losses, is lithium going somewhere where you don't want it.
Okay.
And that's why understanding these systems and the dynamics can be quite challenging, because anything could happen.
Okay.
All bets are off.
All right. Okay. Thank you.
With that exchange, thank you, Sanbin, for actually a great question. Please join me and Will thanking all our speakers for today for being with us.